The second kind of waveguide losses is absorption loss, which happens in semiconductor waveguide. Consider a semiconductor optical waveguide. We have the conduction band and the valence band for the carrier. And the EC and the EV are the band energies of the conduction band and the valence band respectively. We define EG here is the band gap energy between EC and the EV, which is EC minus EV. And if the waveguide mode have the frequency mu, the energy of the waveguide mode can be expressed as E is h mu. If h mu is larger than the bandgap energy Eg, then the carrier will absorb part of the energy of the waveguide mode and to the conduction band. As a result, we will lose part of the energy of the waveguide mode, then this will induce the absorption loss. And such kind of absorption loss is called interband absorption. Besides, carrier will also jump to the temporary band like this. Then, this kind of absorption, we call it intraband absorption. And the loss energy is smaller than the band gap, so h mu is smaller than Eg. But this part will be the main reason which causes the absorption loss. Our purpose is to reduce the interband absorption. For the interband absorption, we know that the energy of the optical waveguide E is h mu, which is in proportion to the inverse of wavelength. And as the energy E is larger than the bandgap energy Eg, then most of the power will be absorbed by the semiconductor material, so we will have large losses. As shown in this figure, you can see that as the input energy is small, we have smaller loss. But if we reduce the wavelength, then we will have higher input energy. And at this boundary, the loss will dramatically increase. Due to here is the corresponds to the Eg. So in this section, in this part, we have E smaller than Eg, so you have smaller loss. But on the right hand side here, we have E larger than Eg, so the loss is very huge. And how to improve this kind of loss? One way to reduce the absorption loss is that we can dope the waveguide with other material. By doping, we can increase the bandgap energy. From this figure, you can see that for no doping, the energy is about the Eg is located about 0.9. But if you have doping 10% aluminium, then the Eg will move to 0.85. And if you dope 20% aluminium, then the Eg will move to 0.8 micrometer. So by doping, we can increase the Eg, then the absorption loss can be reduced. For example, if you operate if the operation wavelength is around this point, then you can see without doping you will have very large absorption loss. But if you use 10% doping, the loss can be reduced to this one, due to you have moved the wavelength corresponding to the EG by doping. Another way to reduce the absorption loss is that if you cannot use doping to increase the bandgap energy, you can just use larger lambda. As you use larger wavelengths, then the corresponding input energy will be smaller than the bandgap energy. For example, as you operate the wavelength at 0.9, for no doping you will have larger absorption loss. But if you move the wavelength to 1.1 micrometer here, then the loss will be highly reduced due to the input energy is smaller than EG. So these are the two ways to improve the waveguide loss by the absorption.